Hi, this is Professor Huang. Today I'm gonna continue talk this private key public key relationship. So we already knew that the input and output, which is private key and public key, they have some kind of relationship. This is 10,000 key. We plotted there the semi-covariance. We'll see the shape like this. So what I did yesterday, I calculate those keys in different quadrant, 2, 1, 3, 4. Yesterday, I calculated the mean, the average, the value of the average. I find there's very little difference. And then I also calculate standard deviation. Still, they have little difference. So today, I actually calculate in a very special way. You can see it's a standard deviation, then times power, standard deviation divided by the mean or average, and then to the a cubic root. So we take the ratio between standard deviation to the average and a cubic root times standard deviation. I'll explain why we do that. This is what we call the state of variance. So this is a variance, it's a 1.5 variance, and approximation, because Excel doesn't give us the formula to calculate our variance, 1.5 variance. So that's an approximation. After we do this, we will find those are in different quadrant. So the variance in different quadrant, and this is the average or for each quadrant. That's for the private key. And then if we do the same thing to the public key, for different quadrant, we also got the average. So this is the average of all the public key in that particular region. And then we calculate correlation between these two average, which is the input output, and we'll find Poisson correlation 0.98999. So which means the input and output of private key and public key, their variance, they are 100% correlated, almost 100%. Or the other way, if we look at pattern when we're sorting it, like this one is the smallest, we say 1, this one is second smallest, 2, this one is 3, and that's the biggest, so it's a 4. If we kind of make it order and then trying to find a pattern, we end up the same thing. So this is the average of their number, or sort of like a champion or whatever. So we number them, either number them or sequence them. We get the average for 4 region, and then we calculate a Poisson correlation, still 99608. So anyway, these are the correlation or the average of the keys in different region. As we can see, like this region, they're small, correlation are small. And this region correlations are big. So each region, they have different average. So imagine if we have a key, we just calculate the variance average. We knew this key falls in which region. And if it's this region, maybe we can use an AI to hack it. If in this region we say, forget about it, we can make it. So that's a way to allow us to decide whether we're going to go ahead, hack it or not. And now I'm going to explain how I come up with those strange formula to calculate. So if you can go to the qmath.com, you will see these kind of formula, binomial expansion. So when powers are rational number, well, 1.5 obviously is a rational number, you can expand the formula in this way. So we see this is kind of expansion as long as x less than 1, which means as long as the some number are not out of the bound, you're able to approximate it. So here we actually focus on this term, the second term, is the x squared. We don't care about x, because this is a mean. And this is a high third moment. You can have fourth moment. But now we just focus on the second moment because the standard deviation is here. And if you go to Wikipedia looking for center moment, you will see this description as well. And actually, third moment, fourth moment, there's a name for it: skewness and a kurtosis. So variance, skewness, kurtosis. We're not gonna bother us for skewness, kurtosis, although we can do the approximation, trying to approximate it with this 1.5 variance, because the normal variance is a 2. This is a Gaussian variance. This is a third moment, this fourth moment. So they have a relationship. Third moment is related to the second moment. And then this is a variance we're playing right now. So if you're using the previous two formula, we were able to simplify 1.5 variance. We call it Steeder variance. So this is the 1.5. Normally we say 2 and a 2. So but now we're trying to figure out a 1.5. I already explained why we do 1.5. It allows us to distinguish different key pairs. If you're using 1, 2, 3, 4, you're not able to distinguish the key pair, but if you're using 1.5. However, 1.5 is too complicated to calculate in Excel. So here we do some approximation. So you have a first term, and then there's some coefficient here. We ignore it. And then you have an average, a standard deviation, and then you have to reverse it to make it looks like a standard deviation again. And then after some operation, you end up approximating. This one is approximate equals that. So that's where the formula in the Excel comes from: STD divided AVE, and a cubic root. So if you do operations, insert this into here, make use of this expansion, and then throw away the not the important part which we don't care, you end up here. And if you want to go further, you say, oh, wait, I need to encode a skewness. If you use a MATLAB, you can do that. You can calculate a skewness. And this is a formula 27/48, and STD square, and then divide by mean. This is the mean, and times skewness divide by mean square, because this is third moment. So you have to divide by twice to get back to the ground. But there's you may ask where this 27/48 comes from. It comes from this formula. So if you calculate, you insert a 1.5 into here, you'll end up with those 48. So that's where the number, also you have to use in this formula as well. So this formula, U3 prime, U2 prime, you have to insert everything all together, you'll end up here. By the way, this is AI machine learning code trying to solve time series prediction. It's a multivariate. So you have a multiple, it's sort of like a multi-polynomial. So you have a univariate and a multiplying time series. And then this code is made by him, a student from Florida University. And I just take his code and do some modification so that we are able to make use of this 1.5 variance, as well as actually we also include a sinc filter. That's for predicting the stock market. So that's Professor Zhou's sinc function. Okay, I will stop here. Thank you.